My name is Pawicha Phairatchatniyom. I'm glad to participate 2022 International Conference Computational and Mathematical Methods in Science and Engineering, and the second conference on high performance computing. My data is a modified Ishikawa iteration for solving split variational equation and fixed point problems. In this presentation, I have 4 sessions. The first session is introduction and motivation. In this study, we consider the fixed point problem in a real Hilbert space S. That is, it is to find a point in a Hilbert space S such that it is equal to its made under a single value mapping T, and we use fixed T to denote the set of fixed points of T. There are many authors introduce several iterative methods for solving the fixed point in the Hilbert space. In this study, we focus our attention to the Krasner-Sierski iteration, which is defined by the equation number 1.2, where alpha n is a constant in the closed interval from 0 to 1. The next one is Mann iterations. We sometimes call Krasner-Sierski Mann iterations, which is the sequence n defined by the equation number 1.3, where sequence alpha n is a sequence in closed interval from 0 to 1. We know that Mann iteration is a generalization of Krasner-Sierski iteration. The last one is Ishikawa iteration, which is the sequence yn and Hn defined by the equations number 1.4, where alpha n and beta n are real sequence in closed interval from 0 to 1. And we know that Ishikawa iteration is a double Mann iteration. Very recently, Berlinde introduced a new single value mapping T called B enriched nonexpansive, such that there exists a non-negative constant B satisfying the inequality number 1.5. And he introduced a modified Krasner-Sierski Mann iteration for solving the fixed point of B enriched non-expansive mapping T. Next problem is split variational inclusion problem. This problem is to find a point x bar in first Hilbert space S such that 0 point in the first Hilbert space S belong to B1 of x bar, and 0 point in the second Hilbert space S belong to B2 of ax bar, where A is a bounded linear operator and B1 and B2 are set value maximum monotone mappings defined on Hilbert space S1 and Hilbert space S2 respectively. We use omega SVIP to denote the set of split variational inclusion problem. The last problem is split variational inclusion and fixed point problem. This is the split variational inclusion problem together with the fixed point problem, and we use a fixed T intersection omega SVIP to denote the set of solution of split relational inclusion and fixed point problem 1.8. We know that X bar is the solution set of a split relational inclusion problem if and only if it is a solution of a fixed point problem in equation number 1.9, where gamma n is a positive step size constant, I is identity operator, and S star is the adjoint of abundant linear operator A. And J lambda B1 and J lambda B2 are single value resolvent operators. For solving the split relational inclusion problem, Berndt introduced the sequence N defined by equation number 1.10. They show that if step size belong to this interval, then the sequence N defined by equation number 1.10 converges merely to a solution in the problem of a split relational inclusion problem. In 2016, Jehu and Abusi introduced the modified man iteration for solving the split relational inclusion problem and fixed point problem for a capacitively pseudo-conjunctive, which is defined by like this. They show that if step size gamma n belong to this interval, and then the sequence Xn converges strongly to a solution of the problem of a split relational inclusion and fixed point problems. In this study, we present a modified Ishikawa iteration for solving split relational inclusion and fixed point problems for the B enriched nonexpansive mapping. The next section is main results. This is our proposed algorithms. We can see that we use the idea of Berndt algorithms and the modified Krasnodębski man iteration of Berndt and Jehu and Abusi iteration, and also we use Ishikawa. We use idea of Ishikawa iteration. The observation 2.2 is construct for the analytical proof of the algorithm 2.1. However, we omit the proof in this presentation. The third section is the numerical experiments. We consider the first example where with the closed interval from the minus to minus 1/2 and mapping TA B1 and B2 defined by like this, and we can show that T is 2/3 enriched nonexpansive. And we compare our algorithm 2.1 with Krasnodębski iteration 1.2, and we surely use KRAS and Berndt algorithms 1.6 with the Charlie form BERI, and we set parameters for each algorithm as follows. And we consider two cases. The first case, we consider the different case with fixed mu. Consider the difference values of mu, and we fix starting point. Figure 1 shows that the Krasnodębski iteration, Berndt iteration, and our algorithm 2.1 depend on the starting point. However, our algorithms convert very fast than other algorithms. Figure 2 shows that Krasner-Sesky iteration and Bernoulli iteration depend on the value of mu, but our algorithm 2.1 also depend on the value of mu, but is lessly depend on the value of mu. Next example, we consider the following 2 and 3 dimensional Euclidean space where operator A, B1, B2 and T defined by like this. In this example, we consider our algorithm 2.1 with the Chehu and Abusi algorithm, and we with Charlie from SHOG, and we set all parameters for each algorithms like this. The figure 3 shows the accuracy of our algorithm 2.1 and Chehu and Abusi algorithm. We see that our algorithm have a better accuracy than Chehu and Abusi algorithm. And also, if we consider the different value of stopping criteria, and we see that after 10 to the power minus 2, our algorithm converges faster than Chehu and Abusi algorithm. The last session is the session of special case. In this session, we consider split feasibility problem, which is find a point star in the set C such that each image under a bounded linear operator A belongs to the set Q. First of all, we recall some important definition for this session. The first definition is an indicator function, which is defined by equation number 4.2. The next one is normal cone, defined by equation number 4.3. The last one is a subdifferential of an indicator function, defined by equation number 4.4. From the definition, we can derive the following properties. And we can apply our algorithm 2.1 to get the algorithm 4.1. And we consider the example in the two-dimensional Euclidean space where set C and set Q defined by like this, and we get the orthogonal projection PC and PQ as follows. In this example, we compare our algorithm 4.1 with Chehu and Abusi algorithm for solving split feasibility problem. Parameter and condition are set as follows. For this is the figure 5 shows that Chehu and Abusi algorithm converge better than our algorithms. These are some references. Thank you for your attention.